Okay, so we're going to talk about sigma and pi bonds. In class, we talked about hybridization, and sigma and pi bonds go along with the hybridization that we talked about in class. So when we talk about a sigma bond, that is end-to-end direct overlap. The electron density is concentrated between the nuclei of the bonding atoms, and they're all single bonds. So the first bond that's bonded is a sigma bond, and then after that we'll talk about pi bonds. It often involves hybridized orbitals, which we learned about in class. And then, so when we have a multiple bond, like a double or a triple bond, we also then have pi bonds. And pi bonds are a vertical overlap of two p orbitals, which I'll show you a diagram in a second, and below atom centers, above and below. They're never hybridized, and a double bond has it has one sigma bond and one pi bond. Okay, so a double bond, the first bond is always a sigma bond, and then every other additional one is a pi bond. So for a triple bond, we have one sigma bond and two pi bonds. Okay? So the thing that it asks you to do is to draw the Lewis structure of C2H4. Okay, so we're going to, hopefully at this point you can do this fairly quickly and understand that carbon gives 4 electrons, each hydrogen gives 1, so we've got 8, 9, 10, 11, 12 electrons that we have to deal with. 2, 4, 6, 8, 10, 12 electrons total in our Lewis structure here, so we have a double bond. The next question says, describe the molecular geometry and hybridization on the carbon in this molecule. Okay, so the first thing that we have to do is we have to understand that this is an AX1, 2, 3, E0. Does everybody understand why it's AX3E0? A is the central atom. And you can pick either carbon, it doesn't matter. And then we have 3 things bonded to that carbon and no lone pairs of electrons. Okay? The hybridization for this one is sp2. Because of the 3 bonds around carbon, it would, and they are equal and it's 120, 120, 120 here. So because of that, we know that it is an sp2 hybridization. All right. So it says, let's see how these how the orbitals make this happen. So we've got our carbon, which is Ne, with a 1, 2s, and 3, 2p bonds. Okay, and so we have 4 electrons here that are able to bond. All right, and when we hybridize, we know here that we have 1 sigma bond here, 1 sigma bond here, and 1 sigma bond here, and then this bond right here is a pi bond. Remember, pi bonds never hybridize. So the only things that are hybridized here are one of the bonds to the carbon-carbon, one of the hydrogen-carbon bonds, and another hydrogen-carbon bond. So that's an sp2. So what happens here is this electron, and this electron right here, they're all the same energy. And it's an sp energy. sp2. sp1, p2. So this is our sp energy. And then the pi bond here is not hybridized, and that's this 4th electron right here is a pi bond, and that pi bond is just the p electron. So the sp kind of meets somewhere in the middle between the s and the p, and then the p is again just like it normally is. So there you've got your S and P, sp2, your 3 electrons, 1, 2, 3 here, that bond equally, and then the pi bond is a little bit higher energy. So it says, can we draw an orbital picture? Well, I have a diagram here of the orbital picture, and you can zoom in if you want to. But here's the deal. So remember, we've got this guy right here. This is a hybridized. This is a hybridized. and this is a hybridized C. The ones that I colored in blue are the sp hybridized electrons here, okay? And then these, the vertical ones, are the pi bonds. This is a pi bond. This is a pi bond, creating our double bonds here. Okay? So this is one of the bonds, and this cloud is the other bond. So, and the hydrogen, of course, is not hybridized. It's just the 1s here and the 1s here. But this is an sp2 hybridized, sp2 hybridized, sp2 hybridized, and this is the p electron. Okay? So let's try another one. Draw the Lewis diagram for C2H2. Describe the molecular geometry, hybridization, and bond angles. So for C2H2, it's C, triple bond, C, H, H. Okay, that's the Lewis structure. So around our carbon, this is an AX2E0. AX2E0 is linear. Okay, the hybridization here, since we have two things bonded to the carbon, that is an sp hybridization. One s, one p, one electron from the s, one electron from the p, come together and form an equivalent equivalent energy electrons of 1sp. And then the bond angles, of course, are 180 degrees because it's linear. Okay, so what we see here when we draw this is we're going to see, and I drew it, or I pulled it in from down here, is we've got the blue ones here are our sp hybridized. Here's the sp hybridized electrons, right? And then we have the two pi bonds, and this is one of the pi bonds. This is one of the pi bonds. And then this is the other pi bond. So we've got this, which is the sigma bond in the middle, and two pi bonds, which gives us our triple bond here. So how many sigma bonds are there on one carbon? Okay, well, there's one sigma bond here and one sigma bond here, which makes us have two sigma bonds on each carbon. And on each carbon, we have 1, 2 pi bonds. Okay? All right. So, question 14 says label the hybridization at each of the different atoms. So here, this carbon right here has 3 hydrogens bonded to it and a nitrogen. If it has 3 hydrogens bonded to it and a nitrogen, that means it has 4 things bonded to it, right? And so what that means is that all 4 of the s and p electrons from carbon are going to be part of that hybridization. That makes it an sp3 hybridization. Okay? So B is nitrogen, and nitrogen has 1, 2, 3, but it also has these 2 electrons right here. So that is also an sp3 hybridization. C, this nitrogen has 1, 2, 3, and remember it has those 2 electrons right there, are part of the hybridization. So this one is no longer an sp3 because remember we have this guy right here that is not part of hybridization. So if that's not part of hybridization, what it is it has this one is part of the hybridization, this one is part of the hybridization, and these are part of the hybridization, so that's an sp2. All right, D, this carbon right here has 1 bond here, 1 bond here, and one of these bonds here, which is hybridized, so therefore this is an sp2. How many pi bonds are in the structure? Well, this is really kind of easy to look at. We've got anything that is a double bond, one of those is a pi bond. So we've got 1, 2, 3, 4 pi bonds. Okay? All right. The rest of this is pretty straightforward. You've probably done something like this before when we were quantifying. Oh, we're going to skip this. We'll come back to it. But when we're quantifying bond, when we're talking about polarity. So go ahead and read through this stuff. I'm going to read it really quickly. Bond and molecular polarity has to do with electronegativity. Okay, remember electronegativity is the measure of from 0 to 4 of the atom's ability to attract electrons. Okay, and also the most electronegative elements, you need to memorize those off the periodic table, are fluorine, oxygen, nitrogen, and chlorine. It's very important because ultimately with the bonding it's really important. Also, remember electronegativity trends and what electronegativity values tell us. If you read this, this is a description, okay? And you're going to need to read through these. Electrons in a nonpolar covalent bond are shared equally. There's no electronegativity difference between the atoms. Most of the time, the one biggie here is diatomic elements and hydrocarbons, okay? We've got polar covalent, we've got ionic bonds. So what I need you to do is I need you to use what you got in class today, the electronegativity chart, and you need to classify each of these bonds as nonpolar covalent, polar, or ionic using the table that you were given. Okay? And then we'll come back and we will finish this up. So hopefully that helps you a little bit. Pause, do these, and then unpause. Here are the answers to the following parts. What you do have to understand here is I got these values from the chart that you picked up in class or something similar. I didn't necessarily use that chart, so it could be slightly off. And then I looked up the values on your table and looked at whether it was nonpolar covalent, polar covalent, or ionic. And all these values line up. And what you have to understand about this one right here is that this one obviously is ionic, okay? So you need to make sure you understand that this is ionic. Of course, it's got a metal and a non-metal, and the math shows that it should be ionic, and it is. Great. The thing that we have here is we show the positive and negative, the partial positive and partial negative sides using this indication right here. And so whichever one is lower electronegativity is going to be our partial positive side. Whichever one is our higher electronegativity is the negative side. And that makes sense because partial or something that is more electronegative is going to pull the electrons closer towards it. Okay, consider the hypothetical homonuclear compound AA. The region describing where the bond electron density is likely to be found looks like what is shown on the right. The size of the nuclei is exaggerated. Nonpolar covalent molecules of a diatomic molecule look like this or like this. So it says figure 1, the figure above on the right represents a heteronuclear compound, AB, right? AB, polar covalent, in which atom A is more electronegative than atom B. Electrons in a bond, what? Spend more time around the more electronegative atom, spend more time around the less electronegative atom, or spend equal amounts of time with both, regardless of the relative electronegativities. Well, I think I spoiled this already and said that it's going to spend more time around the electronegative. It pulls it closer towards it. Suppose both A and B contributed 1 electron to the covalent bond between them. If 2 electrons spent 60% of their time around A, which of the following is true? A will have a fully negative and B will have a fully positive charge. A will have a partial negative and B will have a partial positive charge. Both A and B will be neutral. A will have a partial positive and B will have a partial neutral. A will be fully positive and B will be fully negative. Well, if it's only part of the time, then this and this are not right. It spends it around A and not B, so A is going to be negative because it's the electrons that are the things that are spending. Okay? Now, molecular polarity. We will wind up doing this scenario in class. Well, maybe not. I think I have time to do it now. We're looking at the entire molecule and decide if the molecule is polar or not. If a molecule is polar, it's said to have a dipole or a dipole moment, meaning the molecule itself has a partial positive and partial negative end, kind of like a magnet. Just because a molecule has polar bonds doesn't necessarily mean that it will be a polar molecule. Sometimes polar bonds can cancel each other out and make a nonpolar molecule. Consider the following scenarios. If the bonds are nonpolar, okay, we have a nonpolar bond, the molecule has to be nonpolar. So this right here is a nonpolar molecule because it has nonpolar bonds, okay? Whereas this one is a polar molecule because it has polar bonds, okay? So that's scenario one. If we have just two atom compound and it's a nonpolar bond, it's got to be nonpolar molecule. If it's got a polar bond, it's got to be a polar molecule. All right. So where it comes in and that's kind of funky is when we have more than two elements or more than two atoms in the compound. This one, they all contain some sort of electronegativity difference. So they have the potential of being polar. Here, this is the electronegativity of Cl is 3.5 and C is 2.5. So the difference here is 1 electronegativity for all of these, okay? Now, what happens is the electrons go towards the more electronegative element and they're positive down near the less electronegative element. When they pull in equal but opposite directions, the vectors cancel out, making it nonpolar. So this one pulls in equal but opposite directions, so this becomes nonpolar. Even though it's got a polar bond to it, it is a nonpolar molecule. Same thing here, the electrons go out towards the more electronegative element. Because they're equal but opposite, they cancel out and become nonpolar. Same thing here. They're going to go boop, 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 and because of that, they are nonpolar. Remember, this is going to be our electronegative element. That's why the electrons go towards it. This is our positive or partial positive part. And because there's not a partial positive end and a partial negative end, that makes it nonpolar. Polar molecules don't have an equal but opposite shift, okay? So we've got electrons going here, electrons going here, and electrons going here, and there's no pull upward. Okay, so what we find here is that this is a polar molecule. The big question here is, can I make one cut and separate all the positive from all the negative? And here I can make this cut. If we erase this stuff right here, I can make this cut right here. One straight cut, and I can cut all the chlorine away from all the phosphorus, and I can make a positive end and a negative end. Same thing here. The electrons go this way, and I can make one cut that separates all the positive from all the negative. Same thing here. So we've got electronegativity going this direction. No, this direction. And so therefore they're equal but opposite. We can cut like that. Equal but opposite, but they're not going to cancel each other out. So therefore we can cut it and it will break apart. So what trend, I want you to answer this question. What trend do you notice about all the polar molecules? What do they have in common? And what trend do you notice about the nonpolar ones, and what do they have in common? And bring that to class, and we'll talk about the take-home message again when you get back. Thank you.